Okay, so for this lecture, which is our last and final lecture, you don't have to listen to my voice for almost an entire year. We're going to jump right into an example, just wrapping up method of sections, looking at a moment frame. And then we're going to go through, I'm going to show you what the advantages and disadvantages of moment frames versus base frames are. And then we're going to go through some examples just to kind of prepare you for going into the exam and your project. The very first thing we're going to do, like I said, is, why don't I actually start the slideshow? So it's going to go funny here for a second because I have to swap. Okay, so the very first thing we're going to do is an example. So do you guys remember we had our braced frame 2 weeks ago when we were looking at axially loaded systems? And we had a brace here. Our bay was 8 meters, or the dimension here was 8 meters, and the height was 5 meters. And we had a 250 kilonewton point load on the side of it. So this whole system is the same, except we don't have our braced frame here. So what stops this whole thing from just tipping over under that load? Well, the reason it doesn't fall over is because we have moment connections here. Most tables and chairs that you see built, they don't have braces across here because we rely on a moment connection right here. So we're going to go through and we're going to do the same thing we did for our braced frame using method of sections, knowing that there must be internal forces here stopping this from flying off into space so that this reaction can get to our reaction points over here. Now the one thing that we did when we looked at our braced frame is we didn't know how much of the load went to this side for our X reaction and how much of the load went to this side for our X reaction. And we left some placeholders there. Hold on, I'm getting a phone call. Sorry about that. I didn't actually even get to the phone in time. My phone, which is sitting right here, I still didn't answer it in time. Okay, so when we were looking at the braced frame, we didn't know how much of the load went to this X reaction and how much went to this X reaction. So we went through and started the process. And then when we solved over here, we saw that there was no way for a reaction to get to this point. And we calculated and saw that it was 0, which left us with the ability to calculate the reaction at the other side. The problem with this system is that it's statically indeterminate. We have a pin and we have a pin, meaning we're going to have an up or down reaction here, an up or down reaction here, and a back and forth reaction here, and a back and forth reaction here. That's 4 reactions. How many equations do we have? We only have 3 equations. So that means we're going to have 4 unknowns but only 3 equations. That makes this statically indeterminate. Unless there's anything we can do to make an assumption here. If you were standing on the ground with your feet shoulder width apart and somebody pushed on you, you know one foot wants to lift up and one foot wants to push down. But if you were on the ice, for example, and you knew you were going to slide, or just at that point where you were about to slide, how much of that load do you think was going to go to this foot and how much to this foot? You can almost imagine the sensation and imagine that they're pretty much sharing the load that makes you want to slide sideways. And that's going to be based for your foot on friction. So what if, because this is statically indeterminate, we need to make an assumption? What if we assume that this reaction and this reaction in the X direction are going to be equal? We don't know what that value is, but they'll share the load out in some way. Now, I am going to show you after we do these calculations when that is true and when it isn't. So right now we're going to start with that assumption and go through trying to solve this moment frame for our reactions and then also our internal forces in the system. All right, so let's make me big, and we can go through and start solving this system. Okay, we have a frame, so this is our moment frame. We have a moment frame that is 5 meters tall, 8 meters wide. We know that there is a moment or a force of 250 kilonewtons being applied at the top. So I'm assuming that's a lateral load of some sort. Maybe it's earthquake, maybe it's wind. We know that this is moment connected right here. We know that there's going to be reactions here. We don't know what the values are, so I'm going to start drawing everything in the positive direction. We're going to call this RY1 and RY2, and we'll call this RX and RX. Remember, that's the assumption we're making, that these two are the same value. And we know that when we do method of sections or trusses or anything like that, sometimes it's nice to label things. So let's maybe, where this has multiple planes, let's label things. Let's call this member A, let's call this member B, we'll call that member C, and let's label our nodes. We'll call that node 1, 2, 3, and 4, just because that might come in handy later while we're doing this. So first things first, let's solve for our reactions. Let's sum our forces in the x direction, where everything in that direction is positive, and we want to know what it takes for this thing to not move or be in static equilibrium. Now this was an assumption we made, that we have Rx and Rx. We said that these two things would be equal. We don't know what the value is, but we're saying they'll be equal. I'm going to tell you that that is true, but it's not always true. I will show you later in the lecture why and when that is true and when it isn't true. So we have Rx plus Rx minus our 250 kilonewtons equals 0. So we've got 2 Rx. There's my calculator. We'll bring our 250 over to the other side. 250 divided by 2. Rx equals 125 kilonewtons. Okay, let's use one of our other equations. We can sum the moments about the z-axis with everything going in that direction being positive. We want to know what it takes to be 0, and let's pick node 1 to spin about. I'm going to put my thumbtack right here. So RY1 passes through it, RX passes through it, the other RX passes through it, RY2 tries to make it spin in that direction, which is negative, and our 250 kilonewtons tries to make it spin in that direction, which is negative. So it looks like we've got minus RY2, and RY2 is 8 meters away, and our 250 kilonewtons pushing in this way, it gets as close as 5 meters away. So we've got minus 250 times 5 meters. And we want to know what it takes for this to be in equilibrium or equal to 0. We can rearrange this. We can bring this over to this side. What am I saying? Both of these are in... Sorry, don't mind me. They're both spinning it in the positive direction. Both in the positive direction, so they're both spinning in that direction, which is the same as what we assumed is the positive direction. So plus ry2 times 8 plus 250 times 5. We'll bring the 250 over to this side. It becomes negative, and we divide by 8. So 250 times 5 divided by 8. ry2 equals minus 156.25 kilonewtons. So that means this is trying to pull up out of the ground. Let's sum our forces in the y direction, with everything upwards being positive. We have ry1 going upwards. We have ry2 going upwards, but we know that it is minus 156.25. And that's it. That's the only thing trying to go up or down. So ry1 equals 156.25 kilonewtons. And it is acting upwards. So this 250 kilonewtons tries to make this spin and push that corner down and lift that corner up. So great, we have our reactions. We know what our reactions are now. Now we can start to go through and use our method of sections. Let's make a cut through member A. All right, so we're going to do a cut through member A. So let's draw our section here. We don't know how far up it is. We're going to label this X. So we're making this cut at X. We know that we have a reaction right here of 125 kilonewtons and a reaction right here of 156.25 kilonewtons. And that there must be some internal forces stopping this thing from moving up and down, sliding back and forth, or spinning in space. So let's draw some placeholders for those internal reactions. It's probably an internal shear force, an internal moment, and an internal axial load that we're going to call A as a placeholder because it's member A. I've drawn it in tension. I don't know if it's in tension or not, but I always draw my members in tension until I know what the force is. That way, if I get a negative number, I'll know that it was in compression. So let's start with summing our forces in the y direction, with everything upwards being positive. Well, I have my placeholder A going upwards. I also have 156.25 kilonewtons going upwards. And those are my only up and down forces here. So I can rearrange this and I get A equals minus 156.25 kilonewtons, or A equals 156.25 kilonewtons in compression. Let's sum our forces in the x direction, with everything going in that direction being positive. And we want to know what it takes for this system to be in equilibrium. We've got 125 kilonewtons going in the positive direction, and we've got our unknown shear going in the positive direction. And it looks like that's all we've got going in the x direction. So V equals minus 125 kilonewtons. Remember, positive or negative doesn't really mean much when we're talking about when we're talking about shear. But it does help us keep things organized until we're done. We have one more equation. We can sum the moments about the z-axis, where everything going in that direction is positive. I won't screw up this time, I promise. And let's make our node that we spin about at node x. So we're going to pick that same way we've done it before. We're going to make it where we've made our cut. So we're going to put our thumbtack right here. So if our thumbtack's right here, V passes through the node, A passes through the node, our reaction of 156.25 passes through the node. The only thing that's left is our moment, which is spinning in the positive direction, and our 125 kilonewtons, which is trying to spin it in that direction, which is the positive direction. So we've got 125 kilonewtons, and it looks like it's distance x from the point that we're cutting. So that means m equals minus 125x kilonewton meters. So it looks like anywhere along member A, there's a compression load of 156.25 kilonewtons, a shear of 125 kilonewtons, and a moment that varies, and its varying value is minus 125 kilonewtons times wherever you've cut it away from node 1. So as this gets farther and farther away from node 1, the moment gets larger and larger and larger. Let's take a look. What is the moment at x equals 0? Well, if we made our cut just right here, m equals minus 125 times 0, or 0. What if we made our cut at, this is 5 meters high, at 2.5 meters? Well, let's see. Minus 125 times 2.5, we would get minus 312.5 kilonewton meters. What if we made our cut at m, or at x equals 5, so right at the spot where we connect into our next element? Before, we've never had moments at the ends of our elements. So we have minus 125 times 5, we get minus 625 kilonewton meters. That means that moment has to go somewhere. Well, lucky for us, there's a moment connection right there. So it looks like there's somewhere for that moment to go. So let's make a cut in member B now. So let's make a cut through here. So I'm going to draw my frame like this. I am making a cut some distance x away. This distance is 5 meters. We know that we have a reaction here of 156.25 kilonewtons and here of 125 kilonewtons. And this thing can't be moving up and down, back and forth, or spinning in space because the whole object isn't. So there must be internal forces here that stops that from happening. An internal shear force, some internal axial force. I don't know if it's in tension or compression, but I'm going to draw it in tension as a placeholder. And some internal moment. So let's go through and do the same thing we continually do. Let's sum our forces in the y direction with everything upwards being positive. We have our 156.25 going up, and we have a shear going down, and it looks like that's all we've got. Rearrange this. we have 156.25 kilonewtons of shear in this member, and it doesn't matter where we cut along the member, it looks like the internal shear remains the same. Let's sum our forces in the x direction, with everything going in that direction being positive. We've got 125 kilonewtons going that way, plus B going that way, and it looks like that's all we've got. Or B equals minus 125 kilonewtons, or B equals 125 kilonewtons in compression. We can now sum our moments about the z-axis, where everything in that direction is positive. And let's again pick spot X to spin about. We're going to put our thumbtack right there. Okay, if we put our thumbtack right there, our shear passes through the node, so it's not going to cause it to spin. B passes through the node, so it doesn't cause it to spin. We have we have our moment spinning in that direction, and it's positive. So we've got moment, 156.25 kilonewtons. It's trying to spin it in that direction. So if we curl our fingers of our right hand in the direction it's trying to make it spin, the direction I point my thumb will tell me if it's positive or negative. My thumb's pointing into the page, so it's minus 156.25 times, and it looks like it's distance x away. And then we've got 125 kilonewtons trying to spin it in the positive direction, so plus 125 kilonewtons, and it passes 5 meters away. It looks like our moment equals minus 625, so 125 times 5, bring it over, plus 156.25 x. So it looks like the moment varies along member B depending on how far away we get from it. Let's take a look and see what that is at varying lengths along B. Let's look at the moment at, let's do a couple cuts. Let's do it at 0, moment at 2, moment at 4, moment at 6, a moment at 8. All right, at 0, we have minus 625 plus 156.25 times 0. Well, our moment is minus 625 kilonewton meters. Ooh, A had 625 kilonewton meters. So it looks like that 625 kilonewton meters that's in A can transfer to B. There's continuity there in the moment between those two members. Let's take a look at 2 meters away. We have minus 312.5 kilonewton meters. At 4 meters away, oh, our moment is 0. It looks like it was declining and then it hit 0 at the midpoint. And we get 312.5 kilonewton meters. And then at the other end, we're back to 625 kilonewton meters. Okay, it looks like we're starting to learn some stuff about this frame. Let's make a cut in member C now. So let's make a cut somewhere along the length of member C. So, member C. 2, 3, 4, 5. All right, we know that this distance is 8 meters, and this distance is 5 meters, and we're cutting somewhere along its length x. We have our applied load of 250 kilonewtons, because we've cut past where the applied load is now. We know we've got reactions of 156.25 kilonewtons here and 125 kilonewtons here. This thing isn't moving up and down, sliding back and forth, or spinning in space. So there must be internal forces in this member that stops that from happening. We don't know what those values are, but we can draw some placeholders to try to determine what they are, or what it takes to make sure this thing doesn't move. So there we go. We've got internal placeholders for shear, moment, and axial load. If you're wondering why we didn't use axial load placeholders in the ones we did last week, there was no load and our reaction was 0, so they all would have worked out to be 0. So you could have done that. You could have used the placeholder for the member for an internal axial force, but they all would have worked out to be 0. Let's sum our forces in the y direction, with everything upwards being positive. We have 156.25 upwards minus, ignore that, minus our internal axial load C, and that's it. Must be equal to 0. C equals 156.25 kilonewtons, and we guessed that it was in tension, and we got a positive value, so it is in tension. Let's sum our forces in the x direction, with everything going in that direction being positive. We've got 125 kilonewtons going in that direction, so it's positive, minus V going in that direction. We can rearrange this and we get V equals 125 kilonewtons. So it looks like it doesn't matter where we cut along member C. It's got an internal tensile force of 156.25 kilonewtons and an internal shear of 125 kilonewtons. We have one more equation that we can make use of. Let's sum our moments where everything going in that direction is positive about the z-axis, and let's do what we always do. Pick member, or the point x that we're cutting to cut about, or spin about. So we're putting our thumbtack right here for this. All right, our C, our internal axial force for member C passes through it, so it doesn't cause it to spin. Our internal shear passes through that point, so it doesn't cause it to spin. We're left with our internal moment, 156.25 reaction, 125 kilonewton reaction, and our applied load of 250 kilonewtons. Okay, so our moment causes it to spin in that direction, so M is positive. Putting our thumbtack here, our 250 kilonewtons causes it to spin in that direction, which is positive, so plus 250 kilonewtons, and it is x distance away, so times x. We have our 156.25 kilonewtons trying to spin it in that direction, which is negative, so minus 156.25 times 8 meters. And then we also have our 125 kilonewtons trying to spin it in that direction, which is positive, so plus 125 kilonewtons times this distance here, because it passes along this plane. This total distance is 5, and that is x. So that distance is actually 5 minus x. That's what that distance right there is. We could even fill that in if we wanted. And we want to know what it takes for the sum of all of these moments to make this thing not move. We want the sum of all of these to be 0. Okay, so we can start to work things out here. We have m equals minus 250x plus 156.25 times 8, so plus 1250 minus 125 times 5, and then 125 times negative x would be negative, but we're bringing it over, so plus 125x equals 0. So m equals, we've got minus 250x plus 125x, so minus 125x plus 625 kilonewton meters. Let's take a look at that at a few spots. Let's check it at x equals 0, at x equals 2.5, and at x equals 5 meters. Now remember, we were counting x in that direction. So 0 is here, 2.5 is here, and 5 is down here. So at 0, we have negative 125 times 0 plus 625. Well, we get 625 kilonewton meters. At 2.5 plus 625, we get 312.5 kilonewton meters. And at 5 meters, we get 0. So it looks like at this point right here, we'll have 625, and we go down steadily until we get all the way to the end of the member, and we have 0 moment on it. So it looks like we know lots of stuff about this frame now. Let's draw ourselves some diagrams about it. So I'm going to draw it 3 times. Here we go. So that I can draw the free body diagram, I can draw the axial force diagram, the shear force diagram, and the bending moment diagram. Alright, so in this one I am going to draw the free body diagram. This one I am going to draw the axial force diagram in kilonewtons. Shear force diagram in kilonewtons, and bending moment diagram in kilonewton meters. Okay, we had 250 kilonewtons of applied load. Here, what I didn't draw in here was my dimensions. So let's just make sure we know that that is 5 meters, and that that is 8 meters. We saw that there was 125 kilonewtons at both reactions there. This pushed up with 156.25 kilonewtons, and this one was trying to lift up. So here's the thing. I can reverse the arrow direction and write the number as positive, or I could have kept drawing that arrow upwards, but then I would have had to write that number as a negative. Okay, let's draw our axial force diagram. For member A, we had an axial force diagram of 156.25 in compression. So we had $156.25 kilonewtons in compression. Our member B was 125 kilonewtons in compression. So 125 kilonewtons in compression. And then member C, which we calculated right here, we got 156.25 kilonewtons in tension. So let's use a different kilonewtons in tension. So now at a glance we can see the axial loads in this system. Let's take a look at our shear values in the system. Well, this member, member A, had a shear value of 125 kilonewtons anywhere along its length. So we had $125 kilonewtons. Member B had a shear value of 156.25 kilonewtons anywhere along its length. $156.25 kilonewtons, and member C had a shear value of 125 kilonewtons anywhere along its length. All right, and then our moment frame diagram. Okay, we had at member A, so member A at 0, what color should I use for this? Why don't I use red? At 0, we had 0. At 2.5, we had 312.5, and up here we had 625. Or minus 625. For member B, we varied from minus 625 to 0 at 4, so we started at 625 at 1, 2, 4, 6. Oh, did I not draw? Yeah, here we are. So at 1, 2, 3, 4, we varied all the way down linearly. And so this was minus 625, and this was minus 625, and this was 625. And then member C, we started at the top at 625, and we came down linearly to 0, so 625. So at a glance, we can see all the internal forces and moments acting on this moment frame system. And that is super duper handy. Now we know that in this system, the maximum moment is 625, and it happens at a connection. You've heard me say that connections for moments are a pain in the ass to make happen. So that adds complexity to this system. We can see what the internal shear forces and the internal axial forces are, and we can see where those loads are applied. So this is a really handy way to illustrate everything we've learned about a system. So let's talk now about moment frames. So when, where, and why do we use moment frames? And what can we change about moment frames? How does manipulating the members in moment frames make a difference? So here's the interesting thing about moments, or loads in general. The stiffer the element, the more load it will attract. So if you have a system where all the elements are the same stiffness, it'll evenly distribute the load. And that is why, in that example we did, when I said that it would share the load out equally between these base reactions, it's true as long as these columns stay the same. We're going to see in a bit what happens when that isn't true. So let's take a look at our moment frame versus our braced frame for a second. So these were our two systems. We had our braced frame, which we analyzed 2 weeks ago, and our moment frame, which we just analyzed. Both of them have pinned reactions at the base because they're sitting on the ground. So they're probably locked into concrete, for example. So these are not going to move in the X direction. We went through and we figured out all the axial loads in this system, and then we figured out all the axial shear and moment loads in this system. I have a modeling software that can replicate exactly what we did by hand. So, I mean, you have to build it, and for something this simple, it's almost easier to do by hand. When these modeling softwares come in handy is when we're doing large, complex projects. So, the first thing we did was, I have to make this smaller. Sorry. I'm going to move me, make this smaller, and bring me back down here to the way I normally am. Okay, you can see that we had the same upward reaction no matter the system and the same downward reaction no matter the system. We assumed that these reactions would be shared out equally in this system. And we got 120, this system determined 125 kilonewtons and 125 kilonewtons. So it seems like our beginning assumption was correct. In the braced frame, the only way we could get a reaction down here was through this braced frame member. So all of that shear, all of that lateral load came out as 250 kilonewtons as the base. So these are things we manually calculated over the past few weeks. Here are our axial force diagrams. So again, these are things we already calculated by hand. Here are our shear force diagrams. We calculated these by hand, so 156.25 and 125 and 125. We had no shear in the braced frame version. And then here's our moment with 125 kilonewton meters at this node and 125 kilonewton meters at this node, down to 0. Here is what it takes. Here's just what the members look like to make this work. So our braced frame, these are the sizes of the members that would work for strength. You guys haven't learned how to do this yet. That would come next year. But these members have an axial capacity greater than the factored load on it. These have a factored, or they have a reduced capacity for axial shear and moment that are greater than the factored axial shears and moments in the system. Look at this. Look at how teeny tiny these members are. Look how big and chunky these ones are. So it looks like there's a lot more steel in this. You guys remember, steel can usually be assessed based on weight. The self-weight of the steel in this system is 8 kilonewtons, and the self-weight of the steel in this system is 20 kilonewtons. So it looks like we've got bigger, more expensive members in our moment frame. But if you wanted a door plopped right here, seems like this is a really good way to go about it. But here's one more complication. We haven't even talked about lateral load resisting systems. Or, sorry, we haven't talked about lateral deflections with this. These are our two lateral load resisting systems. We haven't talked about deflection with this. Let's take a look. If I didn't do anything else to this and I looked at how much it deflected, this isn't to scale, so don't freak out. This is not visually how much it would move. The braced frame moves 8.3 millimeters, and our moment frame moves 56.3 millimeters. So at the top of that moment frame, we would see under that 250 kilonewton load, we would see over 2 inches of movement. That's a lot of movement. If you guys remember that the deflection limit that we talked about way back in lecture 1 for wind loads was h divided by 500. We have a 5 meter tall frame, so that means we're only allowed to have 10 millimeters of deflection. So that 56.3 millimeters of deflection is way too much deflection. So I went back and figured out what sizes our members needed to be to make deflection work as well. We already had it work for strength, but this now is what it takes to work for strength and deflection. Our brace frame already worked. When I made it work for strength, it already met our deflection criteria. The moment frame needed to get even bigger, and look at this, more than 5 times the weight of steel to make it work for deflection. So moment frames, you can use them, but they come at a very big cost. Should you never use moment frames? No, that's not what I'm saying. You as the architect have a bunch of different criteria that you need to worry about as well. And aesthetics can definitely be one of them. But I am here to tell you what the cons are to a moment frame. That they're big, and they're very, very expensive, and they still move more. So even with that, this one's still moving just a little bit more. So you can see how much more steel we have in it, how much bigger the members are, and it still moves more than our brace frame. But we're less than that 10 millimeters of allowable deflection now. So moment frames aren't a place we start. They're kind of a last resort if you have other criteria. Maybe you need that door there. Maybe there's something happening there. Maybe that is the entrance to your store. There are good reasons you wouldn't do it, or good reasons why you would do a moment frame. Let's take a look at a few other interesting things that you can do or think about with a moment frame. Well, in summary, they're bigger, heavier, and deflect more. I think I already said that. Let's take a look at this. I've run the same system where I put a pin here, so this is what we had just done. This time I moment connected this to the ground. Great! Look at this. I've made it work for strength and stiffness, and I've reduced my steel tonnage almost by a half. So great, problem solved. Let's always do that. Except that moment has to go somewhere. If that's into foundations, we've got bigger foundations now. Maybe there's something else there and it's not a problem, but we have to be savvy and smart and think about where that load is going. Maybe we have a big, massive concrete wall here. If so, this might be no problem to achieve. Maybe we have delicate little sonotubes here. If so, this is not the way to go. One of the other things we could do to make this moment connection happen here is we could put a member across. We could do this. We could put a member across. The member still didn't seem to work, or it added a ton of steel weight to the system. So yeah, if you look at it in isolation with the moments there, it's great. Except we've just moved our cost to somewhere else in the system now. What else could we do? What happens if we vary the stiffnesses in our columns? Remember I said that if we assumed that that load at the base, our X load, was being shared equally between the columns. Well, if those columns are different stiffnesses, that's not true. If these two columns are the same, that assumption is correct. If not, what these systems actually do, is they apply the load, they make an assumption, analyze it, and see what the loads are. Then they go back and rerun it and see what the difference in the loads are using different kind of distribution of loads. And it goes through that in several iterations until it hones in on the final value. So this is a system where I've made this column much stiffer and this column much less stiff. This is what it looks like to work for strength and stiffness, but let's take a look at what the shear and axial and moment diagrams look at like in our original system versus one with different column stiffnesses. So our reactions, this was our first one. This is what we calculated earlier in the course or in the lecture. Look, we have 185.4 and 64.6 instead of sharing them out equally. Our up and down values stay the same. Our axial force in our column stays the same, but in our member across the top, we have a different axial force. It's a higher axial force. Our shears, it stays the same for this member. It goes up in this column and goes down in this column. And our moments go way down over here, but they go way up over here. If we're having a hard time making moment connections work, this could be a problem. Maybe it's no big deal. Also, look, our point of inflection is where it hits 0, shifts from being at the middle to way over here. I'm not going to test you on anything about these varying stiffnesses, what happens to them, but it does distribute the load differently. So that was what I really wanted to just touch on with you with moment frames. There's not a lot to test you on with that, but moment frames, a lot of people think moment frames are going to save the world. You've got something in your way? No problem, I'll make it a moment frame. And sometimes that is the right solution, but I just wanted to give you the context within that, what it does to the price of your system, and how it moves your loads around if you start to vary the stiffnesses of your columns. So let's move on to some examples now. Okay, let's dig in to some examples that I think will help you guys get ready for your project part 2 and the exam. Again, these are still maybe even one step harder than what you'd see on the exam, because I'm not evil, I'm not cruel. I can tell you that people who have done all of the assignments and have watched all the lecture videos usually do very well in the exam. There are some people who maybe struggle with math and learning that might not do as great, but they'll still do very well. They'll surprise themselves even for a course where you can struggle with math. I find the people that don't do well are the ones that treat the course like a bit of a joke and don't do any prep work. That has been the majority of my experience in this course. So I'm going to tell you that these few examples we're going to do are going to set you up very well to get very good marks in your project part 2 and a fair number of marks in the exam as well. So let's start taking a look at that. Let me just flip through in my thing here. Okay. Before we dig in, I just want to remind you guys about deflection criteria. So there's the maximum amount these are the maximum amounts we'll let beams or elements move. Sometimes they're guidelines and sometimes they are set in stone in the code. The idea here is about comfort and preservation of finishes. Sometimes it can be about stability, drainage, or interface with building elements. But these are the maximum amounts we'll let our element move. Now, the reason I just wanted to refresh this for you with this table is because in the examples and in your project and in the exam, you'll have to tell me what the maximum amount the element's going to move. Because ultimately, we want to know how much we're allowed to have it move. We want to know how much shear force, axial force, and moment are in it, so that next term or next year, we can calculate how much it actually moves and make sure it's less than how much it's allowed to move. Calculate the actual axial load and make sure it's less, or calculate the axial resistance or capacity of the element and make sure it's greater than the load. We want to be able to calculate the capacity of the shear value and make sure it's greater than the factored shear. We want to calculate the capacity for moment and then make sure it's greater than the factored moment. So this is really, at the end of this lecture, you're going to be able to do that 1/2 of the equation for all our elements of strength and for stiffness. So if you guys remember earlier in the term, we looked at a building that is a really weird building that no one would ever build because it's kind of ridiculous, but it allowed us to talk about what drawings look like, and we're going to do some examples pulled from that drawing set. So we're going to take a look at RJ01 and RP02, RB11, and RB03, I believe it is. I have it called up here. Yeah, and RB03. And we're also going to look at column B4. Now all of these beams are in the roof. This one's interesting. This one's simply supported, and we treat these joists as a uniformly distributed load. RJ01 and RP02 are the same length, and they look like they have the same tributary width on them, spanning, picking up the same roofing system. So they look like they'd almost actually even be similar to each other, and they're simply supported. RB03 starts here, continues all the way to here with a column right here. Looks like there's a back span on it here, so it's picking up tributary width from all of this decking, and then possibly has a point load out here from RB07 and RB08 on it. Our column B4 is picking up the roof, so 1/4 of this, but then look, down here it's picking up 1/4 of this bay, but also 1/4 of this low roof. So this is level 2, but this was a low roof on our building, if you remember. And then I just want to talk to you about RB13 for a second. So it's got a column here and a column here, so it's a simply supported beam. But look at this. This isn't a column below. Do you guys remember that CA means column above? It looks like this 2B13 is picking up a massive point load right here. So let's dig in and start talking about our, actually, you know what? I might not even do it as a calculation. I wonder if it's, since I've got it all worked out here, if it makes sense to just talk through it like this. Let's take a look here. I think you guys don't need to see me work through these calculations. Let's make this the biggest it can be so we can really dig in and look at this. I'm going to even move this out of my way here. Set that down. Okay, so we have our column B4. We know it picks up some of the roof and some of level 2. And then a part of the low roof as well. I have drawn here for you guys, I've highlighted the tributary areas that column picks up. So look at this. The first thing we should always do is, if we were trying to draw this on a set of drawings, we'd want to draw something reasonable. So we take a look at our sizing guidelines. If you go back and look at the datums for that drawing, it shows a height of 3 meters for both floors. So our sizing guidelines for a steel column is the height divided by 20, or 3 meters divided by 20 gives us 150 millimeters. So that means we probably want to suggest a 152 by 152. An HSS 152 by 152 seems like a reasonable thing to put on a preliminary set of drawings. So let's take a look, let's break down all the different loads we know are on this. Our high roof, if you go back and look at those drawings, which you can open up, they're uploaded into the FTP site, or not to the FTP site, in Quercus, so you have access to those drawings. The high roof had a dead load and a snow load. Now look, they gave us the snow load. You guys remember that earlier in the term, if we knew the location, we could look up SS and SR and calculate what the snow load is. But on a set of drawings, we have the actual calculated snow load. So somebody's already done that work for us with SS and SR. So somebody's already told us that the snow load for that roof is 1.12 kPa. This 1.32 kPa it comes from adding up all of the roof load components. I think, oh, it's not shown there. But if you look at those drawings, you'll be able to see that we add up all of the high roof load components. The tributary area for both of those is the same. It's a quarter of this bay. That was 9 meters, and that was 9 meters, or 9 divided by 2 times 9 divided by 2. So we can calculate what from second to roof the dead load is on the column, and it's 26.7 kilonewtons, and what the snow load is 22.7 kilonewtons. Level 2, we had some of the level 2 floor and then some from the low roof acting on it. So if we add up all the level 2 dead loads, we get 2.95, and it is acting on an area of 20.25. So we can calculate 59.7 kilonewtons acting on the column from level 1 to level 2 due to the dead loads of this portion of level 2. The live load is 2.4 kPa, same area, but this is a non-assembly load, and look at this. We're just over our 20 meters, so we get to make use of our live load reduction factor. It's probably not going to make much of a difference if it's only just a smidge over 20 meters squared, but we might as well add it in. So 2.4 kPa times 20.25 meters squared, but then we get to multiply it by our live load reduction factor, and we get 48.4 kilonewtons. We have some dead load and snow load acting on this column due to this low roof. We have 1.32 kPa times 9 meters divided by 2 times 3 meters divided by 2, and we get 7.9 kilonewtons. Snow load. If you go and look at that drawing set, and here I've done a little snapshot of it down here, the low roof snow load varied from 1.84 kPa at the edge to 3.39 kPa right adjacent to the higher part of the building. So we're looking at this distance here, or sorry, that should say 1.5 meters, not 3 meters. So I'll go back and fix that. So I'll write a little note for myself on the low roof. I want something that says 1.5 meters. So we're really just concerned about what the snow load is from here to here, and we actually want the average of that snow load. So I figured out that at this point right here, the snow load is 3 kPa. That's just, I basically divided it by 4 and figured out what it was at the 3/4 points and made sure I added it back onto the 1.84. Essentially, I interpolated at 3/4 of the way over between 1.84 and 3.39 kPa. So I have 3 kPa there. My tributary area is 6 meters squared. So 3 times 6 meters, I get 18 kilonewtons. So from level 2 to the roof, I only have these loads acting on the column. So I can figure out what my worst case factored load is. So ultimate, dead, and snow, there's no other loads acting on it, so I don't need to worry about anything else. So I get 67.4 kilonewtons. From level 1 to level 2, though, things are a little bit different. I have all of the loads from the roof, but also all the loads from level 2. So I only have dead snow and live loads, so I should probably worry about my ultimate dead live snow combo and ultimate dead snow live combo. So I can add up all my dead loads and multiply them by 1.25. For live and snow, I'll multiply my live by 1.5. And the companion load of snow, I'll multiply it by 1. And I've got snow from the high roof and the low roof. I have ultimate dead snow live. My dead is the same. Now I'm multiplying the snow loads by 1.5 and using live load as a companion. It looks like live is my principal load and snow is my companion, governs from ground to level 2. So it's a different combination depending where we are on the column that governs. I've drawn my free body diagram here with my factored load from the roof drawn, my factored load from level 2. I've got reactions that stop the column from tipping over at each floor, and then I've got a gravity load, or the foundation, picking up all of those gravity loads. So I've got 3 spots where it stops it from sliding over in space. From level 2 to roof, my worst case load combination gave me a factored load of 67.4. And from ground to level 2, my worst case load combination of ultimate dead, live, and snow gave me 231.2 kilonewtons. So here is my axial force diagram of that column. So this is very similar to what I want to see from you guys on your project part 2. Okay, let's take a look at RJ01. We know it was 9 meters long, and it has a simply supported condition, so that means a pin and a roller, and we have a factored uniformly distributed load on it. Its tributary width, well, if you guys remember, let's go back and take a look. This is 9 meters, and we have 1, 2, 3, 4, 5 bays that or spans. That means the distance between each one of these is 1.8 meters, and that means we have 1.8 meters here and 1.8 meters here, and this joist is picking up half of the roof between here and half of the roof between here. So 1.8 divided by 2 plus 1.8 divided by 2, or 1.8 meters. We've already figured out that our dead load on the roof is 1.32 kPa and our snow load is 1.12 kPa. We can multiply our tributary width by the factored version of that, so dead, factored dead, and factored snow, and we get 5.99 kilonewtons per meter. So every meter of length of this beam has 5.99 kilonewtons acting on it, and it's 9 meters long. We have our serviceability load case of 1.8 meters, and remember the only difference in our snow load was multiplying it by our importance factor of 0.9. So I'm going to take that 1.12 kPa for a regular building that was calculated and multiply it by the serviceability importance factor, and my snow is 1.81 kilonewtons per meter. Dead and snow, 1.8 tributary width times my unfactored dead plus my unfactored snow multiplied by 0.9 for my serviceability importance factor, and I get 4.19 kilonewtons per meter. Now, you guys need to do method of sections for this, but I think you guys know how to do that pretty easily. You've done a bunch of them for a simply supported member. We also should double check it against those beam tables I gave you. So I'm going to do it quickly here with the beam tables. We know reaction 1 should equal reaction 2 should equal the maximum factored shear, which is WF times L divided by 2. Or 5.99 times 9 meters divided by 2, giving us 26.96 kilonewtons. The maximum factored moment WFL squared divided by 8, or 5.99 times 9 squared divided by 8 gives us 60.6 kilonewton meters. We know that we have maximum allowable deflections. For snow alone, it is the length divided by 360, or 25 millimeters. For dead and snow, it is the length divided by 240, or 37.5 millimeters. And we know that we tracked these serviceability loads to use with this. We don't know how. That's the thing we're going to look at next year when we do structures 2. But you will need to know how to calculate all of these things right here pretty quickly going into next term or next year. Here's the interesting thing. RPO2 had the same length. It had the same dead load and the same snow load. It had the same tributary width. So that means all of this work is identical for RJO2. It just means that one is going to be, for RPO2, one is going to be a purlin and one is going to be a joist, but all of the values to determine those remains the same. I have worked out 2 more members here in depth for you. You are not going to have in your project anything as complicated as RB11, but I have it here for you to take a look at. I think that's of value for you. This shouldn't be RB11, that should say RB03, I believe. Here is RB11. So RB03 and RB11 for you to take at if you want more resources to double check against. So those have been made available to you as a cross-reference. This is, up until this year, I didn't even do this. So this is something for you to really dig into if you want a little more experience taking a look at how these things work. So that's it. I feel like maybe you should see my face if we're wrapping up the end of the course. That's it. This is all you're going to see me. Let's make this bigger. Sorry, I don't mean to make anyone nauseous by knocking this around here. So we've done it. We've gotten to the end. You guys now know how to calculate all the internal loads in a member. You know how to determine all the loads acting on a building. You know how to figure out the reactions of columns, trusses, and members, and then all of the internal loads acting on those things. You know how to calculate the allowable deflections. That is 1/2 of the entirety of the problem. And you also know how to, without any other major calculations, figure out what's a pretty good assessment for a member to put on a drawing set. So you are half through all of the design problems. But I've given you a key thing here, how to do a preliminary sizing of elements for a set of drawings, for example. I know this has to have been a crazy hard term for you guys. I can't even imagine what you guys are going through. I've tried to make as much allowance for things as I possibly could. I try to answer questions as quick as I could. There was one person I felt really bad who asked a question a week and a half ago, but I think the questions that, or the problems that I solved in this lecture will answer all of your questions. I want you guys all to remember that the TAs are also up against crazy deadlines, and they're working hard mostly on their thesis projects as well. So we're all a little bit maxed now. That said, you shouldn't ask questions. If it's something quick that the TAs can answer, they'll do it. If they can't, they'll forward the problem on to me, and I'll try to get an answer out to you. You guys have your exam on April 13th. I believe it's in the afternoon from 2 to 5. I've prepared that. The TAs and I are going through it again to just triple, quadruple, Googleplex check it to make sure that it's easy for you guys to process and go through and determine the answers. I have proofed this before. It's not the exact same exam, but it is similar to past years so that I do know that the questions are fair and reasonable. I always go through and take a look and see what statistically the answers are for every question I ever do, so I know if one is a good question to kind of keep going on an exam. So in summary, I'm super proud of you guys, and I think what you guys are doing is amazing in these crazy trying times. Quick summary of this lecture. Moment frames, last resort. We don't like them, they're expensive, they're not easy to do, and deflection will often govern the design. We should know how to calculate maximum allowable deflections and lateral movements of buildings and elements. And then the rest of what today we did was examples. So good luck. There is a strong possibility that I'll be teaching you guys in person for Structures 2 next year. I don't think core courses that have everyone in it, even in fall term, will be in person. My elective might be in person, so you might see me around the building, but I don't think things will be in person for the Structures 1 group next year. But there's a possibility that Structures 2 in the winter term will be. If so, I can't wait to see you. If not, you'll have to wait another year to come up and tap me on the shoulder and say hello. Good luck, everyone, and hopefully I see you soon.